Assalamu alaikum. My name is Mobeen Malik and I will use the Verilog HDL on the Quartus software to implement the logic gates, some Boolean expressions, and the De Morgan's theorem. Now for the first code, this is the code for the logic gates, and this is the name of my module, Boolean, and it has the following parameters: X, Y, OR, and NOR, NAND, and so on. Now, from these parameters, X and Y are declared as inputs, and the outputs are declared as OR and NOR, NAND, NOT, XOR, and XNOR. Now, these outputs need to have a relation with the inputs. Now, the relation is defined as their logical operations, as OR is the logical OR operation between X and Y and is declared by this sign. NAND is a collective NOT. This sign represents the NOT, is the collective NOT of X and Y. NOR is the collective NOT of OR. This is a collective NOT of a single function, single input X. XOR has an operator like this, and XNOR is just its NOT. Now, this is just a simple code to implement the logic gates. Now, after implementing the code, the schematic looks like this. These are the two input pins, and these are the declared outputs. This is the AND gate, and this out here is the NAND. When AND is combined with NAND, this is the NOR, which means that NOT is combined with an OR. Same goes for XOR, and this is a simple NOT. Now, after the schematic has been shown, this is a waveform that is used to verify the truth tables that we can obtain from these gates. Now, this is my first input X, which has a frequency of 100, which has a time period of 100 nanosecond. This is my second output, which has the double the time period of about 200 nanoseconds, which makes it possible to have all the combinations for the outputs. Now, AND is off when both X and Y are off, and it is on only when both X and Y are on, as you can see it from here. Now, NAND is just an inverted AND. As you can see, where AND is off, NAND is on, and in places where NAND is off, the AND is on. Same goes for all the other gates like NOR and its original gate OR and NOR are inverted. This is just a NOT of X, which means that the input at X is just inverted at the output. These are the XOR and XNOR, and XNOR, as you can see, works only at similar outputs, which means that it will work only if X and Y are at the same level. Now here the X and Y are at a lower logic, so XNOR is giving a high output, and here both X and Y are high, so XNOR is again high. Now XOR works in quite the opposite way. XOR is high when X and Y inputs are alternate, which means if X is 0 and Y is 1, or X is 1 or Y is 0, this will have an output of 1. So this was the implementation of the logic gates, and next I will show you some of the Boolean expressions. In the previous lab, I used Proteus to implement these Boolean expressions, and for this lab I will use the Quartus Verilog HDL to implement these functions. Now the module's name is functions, and these are its parameters. These 4 will be declared as input right here, and these 3 are the outputs. Each output will define a specific function. Now the f1 is the first function, which is right here. X is basically A, C is Y, and Z is D. Now the first function says that A or C and D. The second function is the not of A and B or the not of C and D. The third function is the not of A and the not of B or the not of C and the not of D, which these or and ands mean that one of these inputs has to be 1 or 0 to give out a specific output. So if I show you the truth table of these inputs, this is the truth table of the first function, this is the truth table of the second function, and this is the truth table of the first function. All of these truth tables have been explained in the previous lab. Here we will only see the Verilog part. So this is the code for the implementation. Now this is the circuit which was built by the Verilog or the Quartus in its RTL viewer. This F1 gives out the output for the first function. Here the first input A goes as an OR, and the second input C and combined with D goes for the first. Similarly, the not of A goes in the second function. The B simply goes as an AND with A with the not of A into the second function, and so on. These schematics have been explained in detail in the previous lab. Now in these waveform we can see that the first input has been given a time period of 50 nanoseconds, the second one 100 nanoseconds, the third one 200 nanoseconds, and the fourth one 400 nanoseconds. These output waveforms are the verification of the truth tables. The first function x plus y into z can be verified from right here. It is actually on whenever A is on. It is off when A is off and X or Y is off. If any one of the X or Y input, which is actually C and D, is off, the output is shown as off. The second function, which was the A complement B plus C complement D, is on whenever the A is off and the B is on, or the C is off and the D is on. So you can see it from right here from this output waveform. Now the third function also works the same way, and it is on when A and B are off or C and D are off. So for the next code and the circuit, we will be verifying the De Morgan's laws. Now for the De Morgan's laws, these are the four inputs that we have. L1 and R1 are the left and right hand side of the first equation, and L2 and R2 are left and right hand side of the second equation. The code is pretty simple and self-explanatory. As you can see, A or B whole complement is the left hand side of the first equation, and A complement and B complement is the right hand side of the first equation. Similarly, A and B whole complement is the left hand side of the second equation, and A complement or B complement is the right hand side of the second equation. This is the circuit which will help us implement the De Morgan's laws. L1 and R1 will be equal, confirming the first law, and L2 and R2 will be equal, confirming the second law. These inputs C and D are left here by mistake, so we can just right away ignore it. These are the inputs that will be used for both the first and the second equation. Now these are the waveforms which are obtained from the inputs A and B. A has a time period of 50 nanoseconds and B has a time period of 100 nanoseconds. C and D can be ignored. Now, as you can see, L1 and R1 have the same waveform, which shows that they are on whenever A and B are off. Similarly, L2 and R2 also have the same waveforms that confirms the De Morgan's laws. I hope my video helped you understand some concepts. Take care. Allah Hafiz.